How to build a quantum computer with 16 trapped ions. This video covers only the essential parts of an ion trapping system. If I receive 50 likes, I will cover the details in the next video. Enjoy it! Let's chat about how to build a quantum computing machine using 16 ions trapped inside a chamber. Ion trapping is an exciting technology, and maybe the future of quantum computing. So, I'll keep it casual and explain everything in a way that's easy to understand. These are fundamental building blocks of a system, a startup, Quantum Lasso, the first Oklahoma quantum computing company in 2025. Getting started, the basics of trapped ion quantum computing. First off, what's trapped ion quantum computing all about? And then how do we trap ions inside a vacuum space? Well, in quantum computing, we use qubits as the basic units of information. In classical computers, we use bits. They're like the bits in classical computing but way cooler because they can exist in multiple states at once thanks to quantum superposition. In a trapped ion quantum computer, we use ions. These are atoms that have lost or gained an electron, giving them a positive or negative charge, as are qubits. There is a whole technical process to create ions, and for now, we skip that. Each ion represents one qubit, and we can control their quantum states using lasers and electromagnetic fields. So, let's go over different ways setting up the vacuum chamber. So, to get started, we need a vacuum chamber. A vacuum chamber that holds the trapped ions. The purpose is to create an environment where the ions can float around without bumping into air molecules, which could mess up their quantum states. The requirements are that we need to achieve an ultra-high vacuum, which means removing almost all the air. We're talking pressures around 10 to the power of -11 torr. Now, a torr is just a unit of pressure, named after the physicist Evangelista Torricelli. So basically, we need a super empty space. Next up, we have to design the ion trap. The purpose is to hold the ions in place using electric fields. We usually use something called a linear Paul trap. It uses oscillating electric fields to confine the ions in a line, kind of like beads on a string. We apply radio frequency, RF, voltages for radial confinement, which keeps the ions from drifting side to side. Think of it as the ions sitting on a bench next to each other. Then, we use direct current, DC, voltages for axial confinement, so they don't move along the length of the trap. That is how we keep the ions from moving around. Choosing and preparing the ions is a tricky business. Common choices are ions like ytterbium and calcium. Ytterbium, abbreviated as Y, B, and calcium, known as Ca, are elements that have properties making them great for quantum computing. First, we introduce neutral atoms of our chosen element into the vacuum chamber. This can be done using an oven that heats the atoms until they vaporize. Think of it as we cook inside a special oven. Second, we ionize the atoms. That means we remove an electron to give them a positive charge. This process is automated using modern ion traps. We do this using lasers tuned to just the right energy to knock out that electron. The rundown of cooling the ions. Before we can use the ions as qubits, we need to cool them down. The purpose is to reduce their motion to almost zero because moving ions can cause errors in our quantum computations. We start with Doppler cooling. We shine laser light that's slightly lower in energy, red detuned, compared to a specific transition in the ion. So then the ions absorb the photons and slow down, effectively cooling them. To cool them even further, we use sideband cooling. Let me explain. This technique cools the ions down to their lowest possible energy state, known as the motional ground state. Next is the process of encoding qubits in the ions. Now that our ions are chilled out, we can encode qubits into them. We use two specific energy levels of the ion's electrons to represent the 0 and 1 states of a qubit. To do this, first, we prepare the ions in a known starting state using optical pumping. This means we use lasers to pump the ions into the desired energy level. The next step in building the ion-trapping quantum computer is implementing quantum gates. It means it is now time to perform some quantum operations. First, let's talk about the single qubit gates. 1. We apply laser pulses to manipulate the state of individual ions. 2. By adjusting the duration and phase of the laser pulses, we can rotate the qubit state to any position on what's called the block sphere, a way to visualize the quantum state. Next is the two qubit gates. 1. We need to entangle qubits, which is a key feature of quantum computing. It is the key element in quantum computation. 2. It means we now need to do gates. One common method is the Molmer-Sørensen gate. It uses bichromatic laser fields, that's two colors of light, to create forces that depend on the ion's spin states. This entangles the qubits by linking their internal states with their collective motion, scaling up to 16 ions and beyond. When we have 16 ions, things get a bit more complex. Now is the time to explain the ion chain dynamics. 1. The ions form a chain, and their vibrational modes become interconnected. 2. We have to consider these collective motions to perform precise quantum operations. That is super complicated process. Let me explain. Individual ion addressing is the essential part of manipulating ions. 1. We need to target individual ions without affecting their neighbors. 2. We do this by focusing laser beams very precisely on each ion. 3. Devices like acousto-optic deflectors, diodes, or tiny movable mirrors help us steer the laser beams quickly. Reducing crosstalk is another key element in manipulating the ions inside the chamber when doing gates. 1. To prevent the ions from interfering with each other, we might slightly adjust their energy levels using magnetic fields. 2. This way, we can address each ion individually based on its unique frequency. Quantum error correction is the next essential element in quantum computing. Errors are bound to happen, so we need a way to correct them. Usually these are the sources of errors are: 1. Decoherence, when ions interact with their environment and lose their quantum properties. 2. Operational errors, imperfections in our laser pulses or control systems. There are some error correction codes we can use, a similar process in classical computers. We can use codes like the Bacon-Shaw code, which is suitable for linear ion chains. First, we perform measurements to detect errors without disturbing the quantum information. Second, we apply corrective operations based on what we find. Now it is time to do the measurement and readout. We use fluorescence detection. First, we shine a laser that causes ions in the 1 state to emit light, while those in the 0 state stay dark. Second, we detect this light using extremely sensitive cameras or photodetectors. By observing which ions are bright or dark, we can determine the state of each qubit. Finally, the control systems and software. Coordinating everything requires precise control systems. 1. We use pulse generators and waveform synthesizers to create exact timing sequences for our lasers and electric fields. 2. Quantum programming languages help us write algorithms that are translated into the control sequences our hardware uses. Now let's talk about the environmental considerations. Maintaining the right environment is crucial. 1. Vibration isolation. We use special tables to dampen vibrations that could disturb the ions. 2. Electromagnetic shielding. We shield the setup to prevent interference from external electric or magnetic fields. 3. Temperature control. Keeping the lab at a constant temperature ensures the equipment operates consistently. And finally, the safety protocols. 1. Laser safety. Lasers can be dangerous, so we always wear protective eyewear and use beam enclosures when possible. 2. Electrical safety. The equipment uses high voltages, so proper insulation and grounding are essential. Future directions and applications. Building a 16-ion quantum computer is just the beginning. 1. Scaling up from 2 qubits to 16. We can connect multiple ion traps to create larger quantum processors. This involves linking ions in different traps using photons, particles of light, to entangle them. 2. Applications. Quantum computers can solve complex problems in chemistry, material science, optimization, and more. These problems are currently impossible to solve with even best classical supercomputers. They can simulate quantum systems that are too complicated for classical computers. Wrapping up the process. So, that's the rundown on building a quantum computing machine using 16 trapped ions. It's a complex but exciting field that combines quantum physics, engineering, and computer science. By carefully controlling ions with lasers and electric fields, we can perform computations that were once thought impossible. Thanks for joining me on this journey. If you have any questions or want to learn more, feel free to reach out.